What's up, everybody? It's Dan from sagemathtutoring.com. Have another video. This time it is a video on sequences and series for one of my students who has a makeup test coming up, and I figured I'd make a video to help him out, going over various problems that he circled on the review sheet. So let's just dive in right now. Okay, so first of all, I sort of cut off the directions here, so I'm just going to read the directions for this problem number 43. In exercises 43 and 44, find a formula for a sub n for the arithmetic sequence and find the sum of the first 20 terms of the sequence. Okay, so not only are we expected to find a formula for this arithmetic sequence, but we're also expected to find the sum of the first 20 terms of the sequence. Okay, so already we are getting into not just sequences, but also series. If we're going to find the sum of the first 20 terms of the sequence, that is a series. A series is when you actually add all those terms up together, and that is exactly what we're being asked to do. So I think now is a good time to bring into play some of the formulas that we're going to need basically for a lot of these problems, but we'll start with this one. So here is a list of formulas that will absolutely come in handy. So as you can see, we have two different kinds of formulas. There's the formulas that pertain to arithmetic sequences and the formulas that pertain to geometric sequences. Now, according to the directions, again, I had sort of read the directions before. This is an arithmetic sequence. That was made clear in the directions. So we're going to be looking at these formulas, of course. Now, this is a formula that enables you, it's a formula for the sequence, which really just enables you to find, the nth term of the sequence. For example, if I wanted to find the 20th term of the sequence, which, by the way, we're going to do soon, it would be a sub 20, and that equals the first term, which in this case is 100, according to them, the first term plus 20 minus 1 times d, whatever d is. Now, d is the space in between the numbers. They provided us with d. It is -3, okay? So that's very nice of them, actually. Sometimes you actually have to go on this quest to find out what d is and so on, but this is a problem where they actually give you d. They give you the first term as well. So this is very straightforward when it comes to coming up with, a formula for a sub n for the arithmetic sequence. So basically the formula would be as follows. It would be a sub n equals the first term, which is 100, plus n minus 1 times -3, because -3 is d according to them, right? So what I would do, and this is just me, you don't necessarily have to do this, but I would simplify this. So this becomes 100 minus 3n due to distribution plus 3, and then I would simplify that further, and we would end up getting 103 minus 3n. For me, that's just a lot easier to think about. And so there we go. We have satisfied the first part of the directions, which says to find a formula for a sub n for the arithmetic sequence. Now we're going to find the sum of the first 20 terms of the sequence. We're going to find the sum of the first 20 terms of the sequence. Now let's look at this formula right here. That's a series, by the way. Anytime they say the sum of the first 20 terms of a sequence, they're basically saying, take note of the series of this arithmetic sequence and find out the 20th, the sum of the first 20 terms. So the sum of the first n terms is going to be n times the first term, which is 100 in this case, plus the last term, which is the 20th term in this case, all over 2. So once again, it's the sum of the first n terms is going to be n times the sum of the first term plus the last term in the sequence, all over 2. So we know what n is going to be. It's the first 20 terms of the sequence, and therefore 20 is going to go right here. We also have the first term of the sequence that was given to us. It's 100. The question is, what is the last term of the sequence? We're going to need to know the last term of the sequence before we apply this formula to figure out the sum of the first 20 terms. So that's often the case with these series type problems, especially with arithmetic. You're actually going to have to do an extra step where you find the last term in the sequence before you proceed. And that's what we're going to do right now. And we're going to do that by using this formula that we just wrote down. So what we're looking for here is the last term in the sequence. We're taking into account the first 20 terms, so we're looking for a sub 20, and that's going to equal, once again, using this simplified version right here, that's going to equal 103 minus 3 times 20, and that will give us 43. So we know that the last term of this sequence, the last term of this sequence of 20 is 43. So it's like you started with 100, and then, the 20th term in this list of numbers is going to be 43. And that makes sense because D is -3, so that means you start with 100, and then you're kind of going down 3 with every, successive number. And then you end up with 43. Okay, so here we are. We have found the 20th term. So now what would be a good idea is to plug, that number into this slot right here. So I'm going to do that right now. Let's, in fact, rewrite this formula. So the formula for the series for the first 20 terms would be S sub 20 equals, and that would be 20. So just know that this number is always going to match this number, times the sum of the first and last numbers in the sequence. And the first number is 100. The last number is 43. And that's going to be all over 2. And working that out will give us, first of all, the 20 and the 2 would cancel, giving us a 10 up there. So that's going to be 10 times 143. That's an easy calculation. 10 times 143 would be 1430, also known as 1,430. So that is actually the answer. Okay, so once again, we came up with a formula, A sub n equals 103 minus 3n. We relied on this formula in order to do that. We then figured out the sum of the first 20 terms in the sequence by relying on the series formula. And in order to do that, we had to use this top formula to find the last term. Okay, so I'm pretty sure my students are going to understand that. Let's move on to the next problem. So the next problem says, find the partial sum, use a graphing utility to verify your result, right? So these are arithmetic sequences also, okay? These are arithmetic sequences. So we want to find the partial sum. So that's basically code for use this formula, okay? We're going to use this formula. This, is a challenging problem to the degree to which you're confused by this sigma notation, but don't be intimidated by this sigma notation. This notation right here basically just means the sum of all of the numbers in this sequence from, the first term all the way to the 10th term. Okay, so from the first term all the way to the 10th term. So that's what you want to do there. So let's go ahead and do it. So as you know, if we're going to find the sum of, the first term all the way to the 10th term, we're going to have to use the series formula, right? But here's the problem. We don't even have the first term or the last term. So we're going to have to figure out what the first term is and what the last term is. I mean, we have this big formula, this expression right here, but that's not exactly giving us the first term or the last term. So we have to kind of figure that out, right? And the good news is it's very easy to figure that out. This is actually, the formula for the arithmetic sequence, or an expression that represents the arithmetic sequence itself. This is essentially the same formula that you would get had you used this. All right, so they're kind of giving it to us right out the gate. So in order to find the first term of the sequence, all you have to do is plug in 1 into this. And in order to find the last term of the sequence, all you have to do is plug in 10 into this. So we're going to do that right now. So the first term, I'll write f. F equals 2 times 1 minus 3. Obviously, that is going to give you -1. And then the last term of the sequence will obviously be 2 times 10 minus 3. And that will, of course, give you, let's see, that's 20 minus 3, that's 17. Okay, so awesome. We have the first and last term of the sequence. So let's now go ahead and rely on our formula right here to figure out the sum of the first 10 terms. So right now we could write S sub 10 equals 10 times the sum of the first and last terms. So that's going to be -1 plus 17 all over 2. The 10 and the 2 cancel. This gives us a 5 right there. So at this point we would of course have, let's see. The 2 cancels, so it's like 16 times 5, and that is 80. That is 80. So there you go. Bam. All right, so for my student watching at home, go ahead and rewind it, pause it, whatever you have to. The same reasoning would apply to all of this stuff. Don't get thrown off by this. This is really 3/4 k plus 1/4. Okay? Don't get thrown off by this either. These are all just arithmetic sequences that are essentially the same formula that you would get over here. So if you want to find, for example, the first term of this sequence, you just plug in 1. If you want to find the last term of this sequence, you plug in 11, and then you use this to take it from there. Okay, so that's how you do problem number 45. Okay, now they are asking for the sum of the first 100 positive multiples of 5. Okay, first 100 positive multiples of 5. Well, it would be a good idea for us to come up with a formula for the first 100 positive multiples of 5. And what I'd like to do is come up with a general formula for multiples of 5 in general. Okay, now here's how that might work. Okay, that might work by writing a sub n, because that's this formula for a sequence. A sub n equals the first term. Well, the first term would be the first positive multiple of 5. The first positive multiple of 5 is 5. All right, and it's not 0, right? It's 5, because 0 is neither positive nor negative. So the first positive multiple of 5 is 5, and that's going to be plus n minus 1 times the space in between each of those numbers in the sequence. So the first positive multiple of 5 is 5. The next positive multiple of 5 is 10. The next one's 15. The next one is 20, and so on. So clearly, the space between all of these is 5, and that is what goes right here. That is D. D is the space in between the multiples. All right, so what I would do then is I would go ahead and just simplify this, right? So simplifying it would give us 5 plus 5n minus 5, and that would turn into simply 5n. Okay, so that is something that is at a certain level of skill. You might have been able to kind of figure that out just out the gate, or maybe even with experience, you'd be like, oh, positive multiples of 5. Clearly, that's 5n. But, at this stage in the game, for my student, I would suggest kind of just relying on the formula. Don't get fancy, don't get, too confident just yet. Just rely on the formula, keep it simple, and then here you are. You have a formula that gives you the positive multiples of 5. All right, so we're going to use this formula, right? They want the sum of the first 100 positive multiples of 5. So let's go ahead and use this formula right here to figure out what the last term would be. The last term, with the 100th term of positive multiples of 5 would be, to use this formula once again, it's going to be a sub 100 equals 5 times the, because it's 5n, right? So 5 times n, which is 100, and that, of course, would give us 500. So we know what the last term is. So the first term of the sequence is most definitely 5. We kind of made that clear before. And the last term in this particular sequence is 500. We just made that clear now. So now we can go ahead and just use this formula right now. And that would be S sub 100, and that equals 100. And the sum of the first term plus the last term, and all of that would be over 2. You get your cancellations going. That's a 50. And we have 505 times 50. And that ends up becoming 25250. So hopefully that makes sense. And by the way, before I leave this slide, I am going to actually talk about using a graphing utility to verify your result. So I will get to that. I'd rather just go through the, the algebra for now. So hopefully that makes sense to my student. We're going to move on to the next problem. Okay, so find the sum of the integers from 20 to 80 inclusive. From 20 to 80 inclusive. Okay. So this one is kind of interesting. This is definitely unlike any of the problems that we did before. The good news is that we can really just kind of cut immediately to this formula right here, S sub n equals n times a sub 1 plus a sub n. Let's actually begin to flesh that out, because we know, it's going to be an arithmetic sequence because it's like 20 and then 21 and then 22, right? So there's a space of, the d in this case would be like 1 because there's a space of 1 in between each integer. In the previous one, there was a space of 5 in between each integer. But, in this one, there's a space of 1 between each integer, and we're going to go ahead and just use this series formula. So I'm going to write that right now. We have S sub n equals n. Now let's kind of get this over with right now. We know that there's going to be a 2 down here. And we also know the first and the last term. I mean, the first term most definitely is going to be 20 because 20 is included. So it's going to be 20 plus the last term, which is 80, because 80 is going to be included. So now the only question is, what's n? And n is the number of terms that you're adding together. Okay, that's the sort of key insight. N is the number of terms that you're adding together. And the question is, from 20 to 80 inclusive, how many terms is that? That's kind of an interesting question, right? So I would propose thinking about it in the following way. So this might be a strange looking graph, but hopefully this sort of helps my student visualize exactly what happens. If we want to find out how many numbers are between, are in the range of 20 to 80 inclusive, there might be the mistaken assumption that the best way to figure that out is to be like, okay, well, 80 minus 20, bam, 60, done. That's how many terms are in this series. But that would be incorrect, because think about it. What is subtraction? Let's say we have a total of 80 things. This whole thing right here, that's all 80, right? And we subtracted away 20. Well, that means we are getting rid of this part, right? And what we'd be left with in that case is 60. But think about it. One of the numbers that we subtracted away in this block right here was 20 itself, but we want 20 to be included, right? So really what we want to do is, you could think of like subtracting 20 from 80 and then you would get 60, but then you want to add back in the number 20, literally the number 20, okay? So really, n is going to be 61, okay? N is going to be 61. So I'm going to literally write that. It's like S sub 61 equals 61, because again, n has to do with how many numbers you're adding together, right? We are adding together 61 numbers. That's going to be 61 times 100 all over 2. And this cancels this time, right? So we would end up with 50 right there. And therefore it would be 61 times 50, and that is 3050. Okay? Also known as 3050. So that's the answer to that one. There are multiple ways of going about this one. Okay, I like this way the best though. Okay, so if my student or if any of you are curious about the multiple ways, you can leave a comment below. So moving on. Oh, actually, before we move on, when it comes to using a graphing utility to verify your result, I'm actually going to link in the description below a great video that sort of talks about how to use your graphing calculator to verify series. Okay. So just look for that link. Moving on. Okay, so exercises 57 and 60, write the first 5 terms of the geometric sequence. Okay, so this is the first time we have to deal with a geometric sequence. All right. Now, geometric sequence clearly is right here in the reference guide, right? We have, actually we have 3 formulas. We have a formula for a geometric sequence. We have a formula for a geometric series when there is a finite series. And then there is the formula for a geometric series when you're dealing with infinite numbers, which is something that's going to come into play later. For now, we want to write the first 5 terms of the geometric sequence, so clearly that really only pertains to this first formula. Now let's take a look at it. That says a sub n, that's actually an n right there, not an r, and that equals a sub 1, which is the first term in the geometric sequence, times r, which is, by the way, called the common ratio, raised to n minus 1. Okay, now that's a big clunky formula. I suggest just sort of relying on it for now. At a certain point, you're going to get used to it. At a certain point, you're probably going to memorize it as well. So nonetheless, write the first 5 terms of the geometric sequence. And we're dealing with a sub 1 equals 4 and r equals negative 1/4. So I'm going to present a way that I like to do, with these types of problems, especially when it gets into like the geometric sequence stuff. To me, that's when it starts getting a little bit confusing. So I like to rely more on like tables, okay? So I don't know of anyone else who does it this way. This is the way that I sort of made up as far as I know, and it has worked very well for me, okay, in the past. So what I like to do here is, if I'm going to figure out the first 5 terms, I create a table where it's like n is across the top row. And what do we want? We want 5 terms. So it's like the first term, second term, third term, fourth term, and fifth term, right? And that is a nice sort of row right across the top, all right? And then I go in here and I'm like, okay, a sub 1 is 4. So they just gave that to us. It's like, all right, well, the first term of the sequence is 4. Yay. You know what I mean? Right there. Boom. And then they're like, r is negative 1/4, right? Well, according to this formula, it's going to be a sub 1, which is 4. We already know that. A sub 1 is 4, times r to the n minus 1. So I'm going to get to that exponent in a second. And this is the part where I really want my student at home to pay attention to this, because once you get the hang of this sort of systematic way of going about it, it's really going to make things a lot easier, okay? So once again, the sequence will be defined by a sub 1, which is the first term, times r, whatever r is, raised to the n minus 1, okay? So I only want to focus on, right now, the fact that there's going to be this moment where you multiply a sub 1 times r. I'm going to not worry about the exponent just yet. And I'm just going to go right across the board, and I'm going to write 4 times whatever r is. I'll leave empty parentheses. There's going to be 4 times something. There's going to be 4 times something. There's going to be 4 times something. And what is that something? It's going to be r, right? Now, r is negative 1/4, so I'm just going to write that. I'm not going to worry about calculating anything. I'm not going to worry about simplifying anything. I am just filling in the pieces where they belong, okay? And now I'm going to worry about the exponents. Now, the exponent should be n minus 1. Well, n right here is 2, so that's going to be 2 minus 1. So that's going to be an exponent of 1. That's going to be an exponent of 2, 3, and 4, okay? So once you kind of get the first exponent, it's easy. You just go up 1 like that, all the way down the line. And then you just pause and take a deep breath, okay? Because you are assembling the calculations that you need in a very organized fashion, okay? So let's continue. On the next line, you could always extend these down a little bit, right? Extend them down. Now, on the next line, we could even draw underneath. We're going to calculate these further. Now, 4 is just 4, right? Now, what's this one? Negative 1/4 to the first power times 4. Well, for those of you at home, hopefully you would realize that would be negative 1. And this is negative 1/4 to the second power. So first of all, that's going to be positive 1/16. So to me, already I'm getting confused. So it's like, okay, I know it's going to be 4 times positive 1 to the 16. So there's no shame in just piecing it together like this, piecing it together. So it says positive 1/16. This one's going to be 4 times negative, what is it? 4 to the third power is, that would be, let's see, 1/64, but it would be negative, right? So I'm taking into account the fact that any negative raised to an odd power is going to become negative, and any negative raised to an even power is going to become positive. So that's kind of part of the trickiness of this problem. And I'm going to actually make this one a little nicer looking. So that's 1/16 right there. And looking at the next one, it's going to be 4 times something for sure. It's going to be positive, and that's going to be 1/4. 4 raised to the 4th power, that is 256. Okay, 256 right there. Okay, so do you see how I'm just kind of piecing it all together? Now I'm going to go on the last line, right? And by then I expect my calculations to be done, all right? So just keep on moving down, you know, no rush, no need to do too much in my head all at once. I'm just going about this in a very organized way. This is 4, this is -1, this is going to be 4 over 16, that is 1/4. This one's going to be 4 over -1, negative 64, right? It's going to be, negative 4 over 64, which really is negative. That's the first thing to take into account. And it will be 1/16 if you were to calculate that. Now, you can already see a pattern here. Look at this, 4 and then 16. I bet you the next one's going to be 16 times 4, which is 64, which is that one, right? So you can see these patterns emerge, which is great when that happens. So this is going to be 1/64. Now, you could always pause the video and just kind of check, 4 over 256, is that 1 over 64? And you will discover that it is. Okay, so really, I mean, we just did it, right? We just pretty much, solved the problem. If you want to, be a little bit neater about it on the quote-unquote final draft, you could just write 4, comma, -1, comma, 1/4, comma, negative 1/16, and finally, of course, the last one would be positive 1 over 64, and that would be the answer. So once again, pause the video, rewind it if you need another example of how to do that, but actually, we're going to do another one soon. So anyway, that's how I would tackle number 57. Let's move on to number 59. Okay, so let's take a look at 59. A sub 1 is 9, A sub 3 is 4. Okay, so this one's different. We're still going to use a table, okay? But they're being tricky with us because in problem number 57, they gave you R. They don't give you R this time. They give you the third term instead. So they're expecting you to find out what R is, okay? So once again, let's rely on a table, all right? Because that is a systematic way of going about things. That is an organized way of going about things, because when it comes to this stuff, it's very easy to sort of get lost in the weeds and find out how things relate to other things. Once again, okay, it's like they gave us the first term, it's 9, boom. But check this out, they also gave us the third term. What is that? That is 4. Now, the question is, what is R here, right? Because we can't just fill out the sequence without knowing what R is. I mean, you totally need to know what R is, right? So the way to find that out is to rely on this one. You can't rely on this one. Don't rely on the first term. I'm not going to explain why, but just trust me for now. It has to do with the exponent becoming 0, yada, yada. But just know, don't rely on the first term to find R. Rely on the third term to find R. And I'm just going to go ahead and obnoxiously write, that, this was, was it the third term in the sequence? Well, how did we get there? Well, it had to have been the first term times R raised to, n minus 1, and n in this case is 3, so that had to be a result of 9 times R raised to the second power, right? So I'm just relying on the fact that it's like, okay, well, every term is going to be the first term times whatever the heck R is raised to n minus 1. Well, this is the first term times whatever the heck R is raised to n minus 1, right? So I just put it there, right? I just put it there. And that serves, among other things, as a reminder of what I need to do now. What do I need to do? I need to realize that 4 equals this, right? So that is officially enough information to go off to the side and set up an equation that allows me to figure out what R is. Now, R squared is going to be 4 over 9, okay? So R, therefore, is going to be really plus minus 2/3, okay? So it could be positive 2/3 and it could be negative 2/3, unfortunately, okay? Because it could be positive 2/3 because, 9 times a positive number, would give us a positive number here. 9 times a positive number squared would give us a positive 4. But check this out. 9 times negative 2/3 squared would also give us positive 4. So actually, I don't see any reason why r can't be either positive 2/3 or negative 2/3. So that is something for my student to take into account. Let's treat it as though it's the positive 2/3 for now. Okay, we're going to treat it at least temporarily with the assumption that it is the positive 2/3. And we're going to go ahead and just kind of fill in this chart in such a way that takes that into account. So this is going to be 9 times positive 2/3 raised to n minus 1, also known as 1. We already know what this term is. It's 4, right? So we don't really have to do much else with this. It's really these that we have to figure out now. So this one would be, of course, the first term times positive 2/3 raised to the n minus 1. So that would be 3 because n is 4 right now. So it's going to be n minus 1, which is 3. This one, it's going to be the first term times whatever the heck r is raised to n minus 1, which is 4. And let's go ahead and just draw a nice divider and do calculations down here. Let's transfer the 9 down here. And let's do this calculation. That's going to be 18 over 3, also known as 6. So that's that one. We already have this one. It is 4. Also, when it comes to this one, let's see, that's going to be 8 over 27, right? 8 over 27. So that's already too much for my brain to think about right now. So I'm just going to write that, right? My student at home, or those of you watching, maybe you're into like doing stuff in your head. I'm not into it. I'd rather just write it down for now and stay in the flow, really. So this is going to be 9 times whatever this is. Now, 2 to the 4th power is 16. So that's going to be 9 times 16. All over 3 to the 4th power, well, that would be 81. Okay, and we're getting close. We are absolutely getting close to the final answer. We will bring another row into play here. And this should probably be the final round. So it's like 9 is right there. We clearly have 6 right here. We have 4 right here. Now, right now, I'm going to work on this. 9 and the 27, there's a cancellation right now. That becomes 1. That becomes 3. So obviously, we have 8 over 3. And over here, we have a cancellation with the 9 and the 81 as well. So it's like that becomes a 9, and that becomes just a 1. So clearly, we're going to have 16 over 9. Okay? And that is it. Okay, that is it. So this blue row is the first 5 terms of, let's see. First 5 terms of this geometric sequence right here. Now, I'd like to say that we can also, on the next row, take into account the possibility that 2/3 is negative. So let's go ahead and do that. All right. I'm not sure if the teacher is going to harp too much on this. I think the teacher should, so, with math, you want to get like super precise about things and you don't want to really leave anything out. So this is part of the answer. The green bracket represents the final answer. This is the first 5 terms that it could be, and the next 5 terms that it could be are as follows. Now, once again, 2/3 will be positive anytime it has an even exponent, right? So all of the columns that have an even exponent would remain the same. So all the columns with an even exponent are the ones that correspond with an odd number up here. So you see an even exponent corresponding with an odd number up here. So like those columns would remain the same. So this becomes 16/9. This one is still 4, and this one is still 9, okay? But the question is, what is the sign of this one, right? Because if this was a negative 2/3, well, guess what? This would have become a negative 6, right? And if this was a negative 2/3 here, well, that would be a negative 8 over 27, and then that would have given us a negative 8 over 3, okay? So in my opinion, the teacher should expect y'all to know that at the end of the day, there are 2 possibilities for the first 5 numbers in the geometric sequence, and here they are. Okay, hopefully that makes sense. Moving on. Okay, so looking at problem number 61, let's look at the directions first. Write the first 5 terms of the geometric sequence, find the common ratio, and write the nth term of the sequence as a function of n. Okay, so they want not only the first 5 terms, but they also want us to actually come up with like the formula. Not these formulas, but this formula. This is you know, the nth term of the sequence as a function of n. All right. Nth term of the sequence meaning, this one, right? So let's dive in by using a table. Okay, so when in doubt, bust out the table and just kind of think it through from there. So once again, it's the first 5 terms, right? First 5 terms. We have 1, 2, 3, 4, 5. And we have n right there. Let's begin our columns. Cut across right there. And looking at this, a sub 1 is 120. So as soon as you know something, just put it there, right? And then it's like a sub k plus 1 equals 1/3 a sub k. Okay, clearly this is the most confusing part. It's like, what the heck do they even mean? This is kind of like the first time that we're having to deal with this weird notation. But it's important for my student at home and for those of you watching, of course, to not freak out when you see something like this. I'm just going to sort of translate what this means. A sub k is some number in the sequence. A sub k plus 1 is the next number in the sequence. So what they're saying is the next number in the sequence is this. Like the future number, it really could be thought of as this. Okay? Now, what do I mean by that? Basically, what they're saying is, like this number right here is going to be 1/3 of whatever came before. You can think of a sub k as what came before. So each number is 1/3 of what came before. That's another way of thinking about it. Each number is going to be 1/3 of what came before. So this number is going to be 1/3 of what came before. Well, what came before? 120. All right? In my opinion, that's probably the best way of thinking about it. This is like each number is 1/3 of what came before. I think you get it. So therefore, this is going to be 1/3 of what came before. So it's like, all right, 1/3 of 1/3 of 1/3 of 120, right? This number is going to be 1/3 of what came before. So that would put another 1/3. So then you'd have a string of 3 1/3, right? You'd have a string of 4 1/3, right? You can kind of see where this is going. Let's be thorough. This number will be 1/3 of what came before. Well, what came before? It was 1/3 of 1/3 of. Let's blow this up. 1/3 of 120. This is me being perhaps unnecessarily thorough with this sort of demonstration of what's happening here. So this is going to be 1/3 of this, right? So it's like, all right, 1/3 of, we'll wrap this up in yellow. 1/3 of 1/3 of 1/3 of 1/3 of this. Now, do you have to do this every single time? Absolutely not. I'm only doing this to really make clear that all this is saying is that each number is 1/3 of what came before. Now, at a certain point, you might just realize, this is going to be, 120. Here's the crucial insight. On the next line, we could say, what's the reality of what's happening here? The reality is, this is 120. This is really 120 times 1/3, right? The next one is clearly 120 times 1/3 squared, right? Because 1/3 times 1/3 is 1/3 squared. This one is going to be 120 times 1/3 raised to the third power, and so on. Okay? So once again, do you have to necessarily draw all these crazy parentheses? No. At a certain point, you're going to get a sense of what's happening here. In fact, the moment you see 1/3 times 1/3, it's like, oh, 1/3 squared. And then you could write it. Okay? So the point here is the fact that your R is very clearly 1/3, right? R is very clearly 1/3 because, once again, if you look at the formula for the geometric sequence, it's going to be some number, the first term in the sequence, times some number raised to a certain power, right? Well, that's clearly what we have going on right now. So the first part of the directions is write the first 5 terms of the geometric sequence. So we're kind of in the middle of that. Let's just go ahead and do that. So extending these down, clearly this one would be 120. This is going to be 120 over 3, also known as 40. That's an easy calculation. This one is going to be 120 over 9, and that's going to be 40 over 3. In fact, each of these, again, is going to be, like, whatever comes next is going to be what came before divided by 3. It's going to be 1/3 of what came before, so the next one's going to be 40 over 6, because this is 1/3 of what came before. Well, 1/3 of 40 over 3 is 40 over 3 times 1/3. So actually that's going to be 40 over 9. I apologize. That's going to be 40 over 9. So that's 40 over 9. And this one's going to be 40 over 27. And let's see if we could simplify that more. I don't know. Certainly 40 is not divisible by 3. 40 is not divisible by 9, and since 40 is not divisible by 3, it's not divisible by 47 either. So this is actually the first 5 terms of the sequence. And again, if you want to be sort of formal about it, you could always write it off to the side. 120, 40, 40 over 3, 40 over 9, and 40 over 27. Now, they did also want, however, us to find a common ratio and write the nth term of the sequence as a function of n. So in other words, write one of these. So that's what we're going to do. So basically, a sub n equals 120, because that's the first term, times 1/3 raised to the n minus 1. Okay, so that is finding the common ratio, which is 1/3, and writing the nth term of the sequence, which is this. This is the nth term of the sequence as a function of n. Here's the function of n. Okay, so that is the answer to problem number 61. Hopefully that makes sense. Let's move on. Alrighty, looking at the directions for problem number 65. Write an expression for the nth term of the geometric sequence and find the sum of the first 20 terms of the sequence. Right, so one thing we could do here, I mean, this one's a little bit different because it's like, we're writing an expression for the nth term. So in other words, we're going to do this again. We kind of just did something like that. Okay, so we're going to write an expression for the nth term. They want an expression. So in other words, they just want like this part. Okay, whatever the first term is times the common ratio raised to the n minus 1. So that's what they want for the first part of this problem. But then they're like, find the sum of the first 20 terms. So that's the first time where we're going to have to deal with this formula right here, series when it comes to geometric. So let's begin with the first part. Obviously, if we're going to find an expression for the nth term of the geometric sequence, well, we want the first term. A sub 1 is the first term. Well, we already have that at 16. So we know that it's going to be 16, times r to the n minus 1, right? So we need R, don't we? We need R. So I would actually, once again, believe it or not, bust out the table even for this one. So let's take a look at the table now. It's kind of a weird table because now we're only dealing with really two numbers right now, a sub 1 and a sub 2. So let's make a table that has just two numbers, okay? And we already have the first term, and we already have the second term. Actually, they give it to us. It's -8, right? -8. But what else do we know about this second term? We know that it was formed by essentially doing 16 times r to the n minus 1. Well, what's n? N is 2, so 2 minus 1 is just 1, right? So that's going to be 16 to the first power. So we know that 16r equals -8. Obviously, that is enough information for us to immediately set up an equation that says 16r, because that's r to the first power, equals -8. And then we could divide both sides by 16. R equals -8 over 16, also known as 1/2. Okay, so it's official. We totally just found the common ratio, which is r, which is -1/2. So we could satisfy the first part of the problem by just bringing this down and rewriting it as 16 to the -1/2 power n minus 1. Okay, so that's actually the first part of the answer when it comes to what they're asking for, right? Because they are asking for the an expression for the nth term of the geometric sequence. Well, we just found it. Here's an expression for the nth term of a geometric sequence. Now, we want the sum of the first 20 terms of the sequence. That brings us into the series section under geometric sequence. So we're going to take a look at that. I'm going to erase all this for now. Okay, so let's sort of get a little bit familiar with the formula that we're about to use. First time we had to use this one. So it's like S sub n. So n is the number of terms that you're adding together, right? So we could already see that's going to be 20, right? So S sub n is going to equal the first term times the difference between 1 and r raised to the n power all over 1 minus r. Okay, so that is a beautiful, beautiful formula that we could use to immediately solve this problem. Okay, now think about what we have. We have n. N is the number of terms that you're going to be adding together. That's going to be 20. So we already have that. A sub 1, we totally have it. It's 16. We have r, it's -1/2, right? In fact, I'm going to rewrite the expression. It says 16 times -1/2 raised to the n minus 1, right? And, that's based on the general principle of a to the a sub 1 r n minus 1, right? So r, it corresponds with -1/2, so we already have r. Here's what we don't have. We don't have r to the nth power. We don't have r to the 20th power. Now, here's the problem. If you were to plug into your calculator, -1, because r is -1/2. So if you were to plug in -1/2, I should say, -1/2, and raise that to the 20th power, you're going to get a really weird, crazy number. Okay? So my strong suggestion is to use the graphing calculator just for the whole thing. Okay? For the whole thing. And I would plug into the graphing calculator the following. I would plug in this into a graphing calculator. 16. Well, let's get clear. Before I talk about that, let's get clear on the formula. It's S sub 20 times equals 16 times 1 minus -1/2 raised to the 20th, right? And that's going to be all over 1 minus -1/2. So that's really what you're dealing with now. If you're going to plug that into the calculator, I would plug it in as the following. I would plug in 16, and it's all kind of across one line, so it could be confusing. 1 minus negative 1/2. And then you do the little caret, right? So that's going to be to the 20th, right? And then wrap that whole thing up in parentheses, and then you're going to divide that. Now, it's okay to just divide this, product, right? It's okay if the division symbol only applies to this parentheses, because multiplication and division is like that, where really you don't have to wrap the whole top in parentheses, because there's nothing but some number times another number here. Now, if that makes you nervous, go ahead and wrap this up in parentheses, like extra parentheses, that's fine. Nonetheless, you're dividing by this difference, right? So you have to really be careful with parentheses here. So it's going to be that. Wrap that in parentheses and then that. Okay? So I would advise something like this in your graphing calculator, and what that will churn out is 10.66. And these, it keeps going like 6666 and then a 5649. So you could just say this is approximately that. Okay? So kind of a weird number, right? But that's how you do that one. Now, could you have used the graphing calculator, the summation feature, denoted by the video that is, or denoted on the video that's linked below? You could have totally used the summation feature. So once again, if you want to use the summation feature on the graphing calculator, just refer to the link that I placed below in the description. That will send you to a great video that really teaches you how to use the graphing calculator in that way. In the absence of that, or instead of that, like what we just did, you could always rely on this formula as well. Okay, so moving on to problem number 71. So taking a look here, let's see, 71. In exercises 69 through 76, find the sum. Use a graphing calculator or graphing utility to verify the result. Yeah, so let's look at this one right here. We can find the sum by, once again, relying on this right here. S sub n equals the first term times 1 minus r raised to the n power, and so on. So let's go ahead and do that. And let's get very clear about what we need, though, right? We're going to need a sub 1. We're going to need r, right? And actually, that's it, right? You're going to need a sub 1, and you're going to need r. So we have to sort of go on a quest right here to figure out, well, what is a sub 1 and what is r? And that's very, very straightforward. A sub 1, well, let's start with r, actually. R is the number that's being raised to n minus 1. Okay, r is the number that's being raised to n minus 1. So negative 4 is clearly r. Okay, negative 4 is r. In fact, I'm going to write that. R equals negative 4. But the question is, of course, well, what's a sub 1? Well, a sub 1 is the number that's currently being multiplied to r, this r raised to the n minus 1 power. A sub 1 is the number that's currently multiplying itself to it, right, or getting multiplied to it. And in this case, a sub 1 is the invisible 1 that's kind of in front here, that's multiplying times negative 4 raised to the n minus 1. So actually, a sub 1 happens to be 1 in the case of this problem, at least. So what we could do now is go ahead and just write our series formula with the understanding that we are looking for the first term all the way to the 7th term. So we're looking for the sum of the first 7 terms, right? So what that means is when we write this equation right here, n is going to be 7, because n has to do with, how many terms you are adding together. And let's take a look at that. So we have s sub 7 equals the first term, which is 1, times 1 minus whatever r is. Now r we already discovered is negative 4, and that's going to be raised to the n power, so that's 7 right there. And that's going to be all over 1 minus r. Okay? So another one that really you could plug into the graphing calculator, which is what I'm going to do right now. And that gives us 3,277. 3,277. All right. Now, two ways of having gone through that. You could use the summation, feature on the graphing calculator, perfectly fine. And the other way is to actually just kind of work this out. Now, there is that sort of awkward moment where you would have to figure out -4 to the 7th power. Okay, so that would be kind of interesting right there. But nonetheless, you could also plug in the whole thing right into your graphing calculator. And either way, it would give you 3,277. So that's the answer to that one. Now, I want to give a heads up about these kinds of problems right here, like 250 times 1.02 raised to the n power. Even though my student did not circle this one, I still want to draw attention to it because that's kind of a weird situation, right? If you want to, for example, I'll put a little marking near it. So we're looking at 73 right now. We have thus far sort of relied on this being in the form of a sub 1 times r raised to the n minus 1. It's that n minus 1 exponent that really beautifully corresponds here. So we could very clearly see that r is -4. R is not as clear right now, or a sub 1 is not as clear, because this is not n minus 1. We can't match apples to apples if this looks completely different than this. So the question is, how can we get an n minus 1 up here? And the way that you could do it is by realizing the following. So first of all, I'm just going to write the expression. It's 250 times 1.02 raised to the n. Now, the question is, it'd be nice to have, 1.02 raised to the n minus 1. That would be nice because then it would match this r to the n minus 1, right? Then we could be like, okay, well, 1.02 is r, and then we could just take it from there, right? But the problem is this is not 1.02 raised to the n minus 1, it's 1.02 raised to the n. But I think one of the things you could do is just get clear about, okay, well, what is this? Like, let's say we did want this. Well, what is that? Well, that is really just this, right? It's 1.02n all over 1.02. Okay, so this equals that. Now, if that's not clear to you, just pause the video, look at it, and make sure that you gain clarity about this. In the interest of time, I'm just going to keep moving, all right? But this does sort of require you recognizing like the laws of exponents and so on, okay? And I'll give you a hint. The bottom line is this has an exponent of 1 hovering above it, all right? So this would turn into that. Now, seeing as how 1.02 equals this, well, why don't we go ahead and just force this thing to be that? All right, now bear with me. We're going to force this thing to be that. Right? But here's the problem. I can't just, and I'll even wrap it in green parentheses. So we're changing this to become that, okay? And I can't, unfortunately, just stick a 1.02 here. I have to make up for it by having it up here so that it would sort of cancel, okay? If I'm going to just magically put a 1.02 underneath 1.02 raised to the n power, I have to put a 1.202 here so that it will cancel that and turn it back into this thing. But what we're accomplishing now by doing this is we're just kind of we're roughing this up so that we can force it to have the n minus 1, right? And what happens as a result is you end up with this becoming, what you want, which is 1.02 raised to the n minus 1. That's what we want. But now we have to multiply these guys together, don't we? So 250 times 1.02 is 255. Okay? So this is what we're dealing with. And at that point, then you can proceed as normal. You have your r your R is totally clear. R, in this case, is, let me just get rid of this. R, in this case, is 1.02, because that corresponds with the number that's being raised to n minus 1. The a sub 1 is corresponding with 255. And then you would just plug those numbers into this formula and you would get the sum, okay? But what's the moral of the story? The moral of the story is that before you proceed with a problem like, 73, you have to sort of force this to have n minus 1, okay? How do you do that? Well, you change this into 1.02 raised to the n minus 1, but then you multiply 250 times 1.02, okay? So you have to kind of bump this one up in order to make that happen, okay? So hopefully that makes sense, and I'm going to move on from here. Okay, so finally, last problem right here. Let's look at it. Let's get rid of this green because it's distracting. So we have 77. Okay, so this is the first time where it's like they're giving you a geometric series, but it's an infinite geometric series. How do I know that? Well, it's like we're looking for not just the first term. Yeah, it's first term, second term, third term, but all the way up into an infinity of terms. Okay, so we want the sum of the infinity of terms in this geometric series right here. So that's kind of crazy, right? So I'm just going to cut to the chase. What you want to do when faced with this is rely on this equation, okay? This is the first time we had to deal with that. So we want to rely on this equation. It's like s sub infinity equals the first term all over 1 minus r. It's kind of interesting and perhaps surprising that this equation is so much simpler than pretty much anything we've done so far, and yet this is the equation that deals with infinity. So that's kind of, an interesting thing. So let's do it. All right, we're going to do it right now. We have 7/8 raised to the I minus 1, and clearly the r in this case is 7/8, and clearly a sub 1 is 1, right? Because what is a sub 1? Well, not only is it the first term in the sequence, but it's also the number that's currently multiplying to r. R is 7/8, and the number that is secretly being multiplied to 7/8 is this little invisible 1 that's in front of there. So you don't want to forget about that. You don't want to forget that there's an invisible 1 there, and that 1 is the first term in the sequence. That 1 is a sub 1. So we're just going to put that there. We're going to put that in the formula. Here's us using the summation series formula for infinity when it comes to a geometric series. It's going to be 1 minus whatever the r is. Well, we already know that r is 7/8. And up top, it's going to be the first term in the sequence, also known as 1, because that is the number that is secretly being multiplied to 7/8 over here, and that corresponds with this a sub 1, which is being multiplied to r. And that's going to end up becoming, I think, I could actually do this in my head. That's going to be 8 over 8 minus 7 over 8, so that's going to be 1/8, and that will be 8. Okay, so you could also use the calculator if need be, but at the end of the day, this one is going to be 8. All right, so that's how to do that one. All of these should therefore be straightforward. As you can see, all the exponents are like k minus 1. I guess that would be I minus 1, k minus 1, right? All of these are very straightforward, so you just kind of use this formula and then you're good to go. Anyway, hope that's helpful for my student at home. Good luck on your test. And for those of you watching, if you have any questions, including my student, please comment below. And if I made any mistakes too, comment below as well. Of course, I could make careless mistakes as I just kind of dive into this stuff. So just let me know, and I will talk to you later.